Hey again everyone. Today I'm going to be taking a look at fine-tuning Stable Diffusion again, because it's been a long time since I've gone into any depth with it. It's tough to give any generalized information about Stable Diffusion training because so many answers are simply, it depends. The dataset, sampler repeats, sampler and optimizer parameters, and any number of training settings can have a huge impact or negligible impact on the training. And one parameter being off can push training into a poor direction, or a couple bad training samples in the dataset can really throw things off. I'm going to be using a dataset with multiple styles, concepts, and characters. This is typically a bad idea, but I find it a lot more interesting to push the extremes of training. Since it's pretty trivial to train a mediocre quality LoRa adapter with even a half dozen images and using a training preset, you can kind of put in next to no effort and get a reasonable outcome. But I want to try to improve on what's already there. Well, that's the goal anyway. So in today's video I'll be going over some of the Stable Diffusion 1.5 and XL LoRA and GLoRA training runs that I've done. For these I'll try to show how some of the parameters have affected the training. To do that, I've had the trainer generate samples frequently during the training run, with a set of prompts and using the same seed. Then I've taken the output images and used FFmpeg to generate some clips. I could have imported the raw images into a video editor, but this is a little more convenient given the number of images. Hopefully this way you can see how the figure changes throughout training, and compare and contrast how different training environments change the outcome. Later on I'll show the results of a test of how transfer learning can be used to speed up training a new character on top of an existing LoRa adapter. For training I'm using the Kohya SS script, running under Windows 10. Originally I was using WSL 2, but decided to try a Windows installation midway through on a whim. The output on the Windows installation, using the same dataset and the same parameters, was much different than the model trained on my WSL2 Ubuntu installation. As far as I can recall, I was even using the same seed for training as well, but I could be wrong about that as I did drop the set seed midway through training. Running on Windows directly gets around the drive slowdown that comes from data transfers between the WSL virtual disk and Windows. Training on Windows was faster, so that may be why. But the quality for the step count was also better when I trained on Windows, and for that I really have no explanation. Though the trainer on Windows isn't using Triton, whereas I think the trainer on WSL was, so the Triton optimizations may be why. But that also may only apply when using the Prodigy Optimizer. I didn't want to go back and repeat training runs to figure out if it was the same with other optimizers, and just moved on to training on Windows directly because of the speed increase. I won't be going over the installation of the Kohya training scripts in this video. There are tutorials out there and the installation instructions on the GitHub should walk you through it. In terms of hardware, I'm running this on a system with a Ryzen 5 5600G, 48GB of RAM, and a 12GB GeForce RTX 3060. Before I get into training, I'll talk a little about the dataset that I'm using for the training run and how I put it together. One of the best tools I've found for image gathering has been the Bing Image Downloader Python package. It has an adult filter that can be enabled and generally does a good job crawling Bing pages to scrape images. Use a few variants of search terms and then move all the files into one directory and select Keep Both Copies. Then download the file deduplication tool DupeGuru, install it and load it up. Add the image path to the DupeGuru search path. Select pictures, and under the options menu you can adjust the sensitivity. Start relatively high and lower it until all the detected duplicates can be moved or deleted. Then I do another quick skim of the images and remove any bad ones. If you want to use an image upscaling or processing tool, I would do it here. Some people recommend Topaz Gigapixel, but there are free alternatives that may have models that can work with certain image types. I'll link to the Waifu2x GUI tool in the description below. Next, I crop the images. I have tried using bucketing for training, but it seemed that a lot of the training data was being discarded or something. Or maybe there were limited samples for certain image sizes and too many for others, and it was being trained inefficiently. Cropping the images just seems to work better, especially when using captions, so I'll be doing that. Many people recommend a browser-based tool for bulk image cropping and resizing called BIRME. I don't mind using a browser tool, but I'd rather have a locally hosted one. Thankfully someone has cloned BIRME and made a few tweaks and put it up on GitHub. Installing and running the BIRME clone is as simple as following the instructions on the GitHub. Load in the images, then change the size to high quality output, set your resolution, and then adjust the crop window on each image. When done, save the images to a zip. For captioning images, the Kohya GUI has a manual captioning tool that will load in the images with a quick list of tags. But I generally find it easier just to use a text editor since I type quickly. If there are common blocks of tags, I'll just copy and paste them, or use regular expressions to find and replace something, or insert text at the beginning of the caption string using Notepad++. In the image caption, I use the trigger word and class name, as well as the proper name for the character or concept as long as it doesn't collide with the general term. For example, in the Alice in Wonderland dataset, the trigger word is Alice Liddell with no space and class name, then the proper name. If it's a character that typically wears the same clothing or outfit, I also use the name and the word costume. Other than a general description of the subject and background, I also include image style tags such as illustration, or in this case animation, as a shorthand for hand-drawn animated frame captures. The bulk of the training here is going to be done using a dataset consisting of about 800 images that with repeats comes to about 900 steps. I did some cleanup of the dataset as things trained and removed a few problematic images along the way. Some have more samples, some fewer. Each subject in this dataset has its quirks, so let's take a look at some of the dataset and how those quirks could affect the outcome. In general, I want a model that'll make some comic book looking images, possibly in a variety of styles like airbrush or line art. We'll have to see what gets picked up from the captions though. I'll go over the dataset characters, some of the images and types, and the rationale for choosing them and how they're captioned. I chose 16 characters sort of at random after searching female superhero on Google. The image counts are approximate because there are few duplicates in the set and still a few images that I want to remove for future runs. For Batgirl, I have a set of fan art and comic book images in airbrush and illustrations with about 50 images in total. The character appears in very different outfits and in very different styles. The modern Batgirl character looks very cartoony. I don't think this would work very well if this was the only set of images I was using for training. With Catwoman, there are about 44 images in a variety of styles from comic book style illustrations to realistic digital paintings. Though the character's outfit is similar in many of the images, there are a few style variations that needed to be categorized or differentiated. There's a mask, goggles, and some sort of eye mask. Also, the Batgirl mask and the Catwoman mask look very similar. If the image is just tagged with mask, like what's done with a lot of the image-to-text auto-taggers, the model would have difficulty differentiating what mask should go on what character, and eventually it would probably fit to a synthesis of both masks. However, tagging the mask as Batgirl mask, Catwoman mask, Batgirl eye mask, Catwoman goggles, etc. seems to keep the concept separate. Catwoman's gloves generally have claws as well, so I've tagged them as gloves with claws. Then added the tag Catwoman costume to tie it all together. Stable Diffusion should associate the character name with each of the tagged objects, but also the common character name costume tag. Harley Quinn is going to be a difficult character to train because there are really dozens of interpretations of the character's look. So let's see how things go using about 55 images from comics in assorted styles. For the character, I've tried taking the common two variants of the costume, which is what I'm calling the Harley Quinn Jester costume, and the crop top outfit, which I've tagged as Harley Quinn costume. Hermione Granger from Harry Potter is a late addition to the dataset. For this character, I'm using photos from the movies and trying to generate sample images that look like illustrations in a comic book style. This is only going to work if the term comic book style gets associated strongly enough from the other images in the dataset. Kim Possible, Lois Griffin, and Meg Griffin are also simpler art styles, so I'll be interested in seeing if the model can keep the detail level for their character consistent. Since I have two characters from the same show, I've also tagged Lois Griffin and Meg Griffin each with the term Family Guy style. We'll see if the style can be carried over into other characters in the final model. Spider-Gwen is about 130 images. Spider-Gwen in the suit was tagged with Spider-Gwen. With the mask off, the character is tagged as both Spider-Gwen and Gwen Stacy. The Gwen Stacy comic book images are just tagged with Gwen Stacy. And the Spider-Verse movie style character is quite different than the comic book, so the movie style character images here were also tagged with Spider-Verse style. Supergirl is about 100 images with both illustrations, TV promo photos, and cosplay photos. The photos are tagged with photo, photograph, and are all tagged with the term cosplay, in addition to the character name and costume. Starlight was a pretty big character on the TV show The Boys, but I'm not sure how large her role was in the graphic novel. I found more photos and illustrations, but the character dataset is about 44 images, with around half being illustrations. Since the word starlight is pretty ambiguous, I tagged the character with "the boy's starlight" as a single word to avoid collisions. Misty from Pokemon is tagged as Pokemon Misty using 25 images, with a few cosplay photos and digital paintings, and fan art. The inconsistency and small size make this a poor quality dataset. I want to see if the strength of the other parts of the dataset will make up for the shortcomings here. The Scooby-Doo characters Daphne and Velma are trained using around 60 images each, using a mix of fan art, screen grabs, illustrations, and cosplay photos tagged similarly as the other characters. Psylocke and Mystique from the X-Men were selected with 50 images each. I think the only thing anyone really remembers about Psylocke is the outfit, which is often a blue or purple revealing leotard. Traditional ninja attire, you know. Mystique has blue skin and sometimes scales, though I think that's more from the movie and later comics. Her character is tagged with blue skin and Mystique leather costume or Mystique dress costume. The dress often has a belt made of tiny skulls, which is an interesting tactical and fashion choice. And Stable Diffusion has a particular difficulty in picking up a belt made of tiny skulls. Wonder Woman is probably the most consistent character in the dataset, with about 96 images in a variety of designs. I deliberately avoided images of the Gal Gadot Wonder Woman as the character was already present in the original Stable Diffusion training dataset. We're going to look at both Stable Diffusion 1.5 and Stable Diffusion XL LoRA models and GLoRA adapters. I'm going to take a sampling of the runs I've done, and if something's wrong with them, I'll try to discuss what caused it. Let's start out with some adapters I've trained for 1.5. With standard LoRA adapters for Stable Diffusion 1.5, I seem to get the most stable results using Prodigy and a network dimension of 128, an alpha of 64, and no noise offset. There are some additional parameters needed to get Prodigy working well. I've set the arguments decouple equal true, weight decay 0.01, D coefficient 1, use bias correction true, and safeguard warmup true. I've also set betas 0.9 and 0.99. From what I understand, adjusting the D coefficient and the second beta value have the largest impact on learning rate, with the D coefficient altering the starting rate and the betas altering the rate of change. I've also tried betas at either end of the extremes with 0.999 and 0.901, and 0.99 seems to allow learning to proceed smoothly with a little less bouncing around. There are a couple issues you might run into when training Stable Diffusion 1.5 LoRA adapters using the Kohya scripts. There are some reports on GitHub of bucketing behaving oddly. Some say the adapter isn't training at all, and in my case I found the adapters training fairly inefficiently, and it seemed as if some aspects of the images weren't being picked up at all. Cropping images and disabling bucketing brings training back to what I expected. I don't recall having the issue with bucketing last year when I was doing a lot of training, so it may be a newer issue, random, due to my environment, or maybe it's just my hallucination altogether. The other potential issue I found is when gradient accumulation is enabled. You'll see a user warning none of your inputs have requires grad equals true, gradients will be none. There was a bug report on GitHub and the author seems to think that it's either fixed or a non-issue, but I was getting slightly worse results with gradient accumulation enabled. Again, this could be nothing, or it could be part of the adapter not being trained. I'm not quite able to figure out what's going on here. LoRA adapter training for Stable Diffusion 1.5 is much less of a headache now than Dream Booth training was back in the early days. With enough training and the right sized LoRA adapter, you can really push the Stable Diffusion model to produce virtually any kind of image type you can think of, as long as you're careful about your images and how they're tagged. Training your new concepts onto existing tokens can speed up training if your images are very similar. Think about the Catwoman and Batwoman mask similarity example from earlier. There is some representation of both characters in the model already, and I'm refining that with the LoRA training. If you train a person on a similar looking character or celebrity, you may get acceptable results in fewer steps than using a random token for the association. In contrast, you may get even worse results if using an extremely dissimilar person and training onto an existing token. Kohya supports a ton of esoteric variants of LoRA. A new one that was particularly interesting was the GLoRA adapter. To quote the abstract from the GLoRA paper, generalized LoRA, or GLoRA, is an advanced approach for universal parameter-efficient fine-tuning tasks. Enhancing low-rank adaptation, GLoRA employs a generalized prompt module to optimize pre-trained model weights and adjust intermediate activities, providing more flexibility and capability across diverse tasks and datasets. Moreover, GLoRA facilitates efficient parameter adaptation by employing a scalable, modular, layer-wise structure search that learns individual adapter of each layer. Originating from unified mathematical formation, GLoRA exhibits strong transfer learning, few-shot learning, and domain generalization abilities as it adapts to new tasks through not only weights, but also individual dimensions like activation. Well, some of that's a bit beyond me. What GLoRA does for Stable Diffusion is minimize concept bleed between subjects, and allows you to more easily prompt across subjects and seems to converge faster and produce images closer to the input than the standard LoRA adapters, especially for complicated datasets. Let's give it a run and see how things turn out with a network alpha of 64, network dimension of 64, convolutional dimension of 32, and convolutional alpha of 32. This one initially looked like it was working well, but midway through the training, progress stalled. I left it training for a long time just to see what would happen, and it was pretty uneventful. The buzz was still variable throughout the samples, so I think it was still learning something, but the detail and logical composition of the images didn't seem to really be improving. Network alpha and dimensions of 64 can produce some reasonable output for a standard LoRA, but it seems like that just isn't enough for this GLoRA. Here's another GLoRA trained using the same dataset with only 2 training parameters altered. The network dimension has been changed from 64 to 128, and the convolution alpha has been lowered to 1. This is still early in training, but the variation in position of the figure is less due to the convolution alpha being lower, and the detail in the images is increased due to the network dimension increase from 64 to 128. This is trained for about 30 epochs, or about 1/5 the time of the prior adapter. But why stop with Stable Diffusion 1.5? And no, I don't mean 2.1 or whatever that was. I mean SDXL 1.0, which can be trained using a 12GB NVIDIA GPU on Windows as long as you're using the recent drivers that support the new Memory Overflow Management System. If you're using the overflow memory, some of the models offloaded to the system RAM once the VRAM is exceeded. This stops those nasty out-of-memory torch crashes, but also enables you to virtually extend your GPU's VRAM with quite a bit of speed trade-off. It's going to be about 10 times slower than using GPU memory. But if it lets me sort of train an SDXL adapter, hey, why not try it out? Training SDXL normally takes about 20 or so gigabytes of VRAM, and using the overflow memory is very slow. SDXL was trained using a variety of image sizes, but the dimensions work out to being a sum of 1024 by 1024 pixels. Training something that large is just too slow on my system using the Prodigy Optimizer, and I want to stick with Prodigy for now. I've reduced my images to 768 by 768 for the SDXL LoRAs. It just takes a long time to train, somewhere between 15 and 30 seconds per step. However, steps to quality, SDXL seems to improve quicker than 1.5 does. This adapter was trained with the network alpha and network dimensions of 64, memory efficient attention enabled, and using the low RAM additional training flag. Once again, I stuck with Prodigy using the arguments decouple equal true, weight decay 0.01, D coefficient 1, use bias correction true, safeguard warmup true, and betas of 0.9 and 0.99. And the learning rates are all set to 1 to allow Prodigy to automatically make adjustments. The scheduler I'm using is cosine with restarts, with the number of restarts equal to however many training epochs I'm doing. SDXL has 2 text encoders that should probably be trained independently, but at the moment this isn't supported by the Kohya LoRA training script. Using Prodigy as the optimizer seems to handle the learning rate well enough that it may overcome the text encoder overtraining issue that some people seem to run into. I'd like to let this one train a little bit longer and see how things improve, but I'll put this one back in the oven later. Right now I want to use it as a base to fine-tune a different dataset. This adapter already has some representation of how I want the weights for things like illustration or comic book style to appear, and it can take a long time to train a new adapter from scratch. But using the weights from an adapter with a similar style seems to kickstart the training pretty well. Here I've used my comic book LoRA as the base by setting the trainer to resume from that checkpoint, and then trained it on the Alice in Wonderland dataset. There's an issue with token collisions here, as there may be actual photos of Alice Liddell in the original Stable Diffusion training dataset. That would explain the bias toward black and white photos on cardstock backgrounds. I can't however explain the lovely flowers. Happy accidents, I guess. This trained much faster than from scratch, and this stretch adapter kept interpolating the missing portions of the blue dress as pink. Well, that's about all I wanted to go over in this one. I cut out some of the compare and contrast stuff that I was going to get into because it was already running a little bit long. If there's enough interest in a follow-up, I might put one together. I mainly want to take a look at the Prodigy Optimizer and cover some of the hidden hangups you might encounter when training. If you found this helpful, please hit the like button or subscribe if you want to see more of whatever this is. Thanks for watching.